Your enterprise is built on an illusion. It is the easy button of automation, the managed connector. We have been told that these pre-built wrappers are the key to velocity, and we buy into the idea that they enable scale. But in reality, they are a trap. Most architects choose them because they prioritize speed over structure, and they want the quick win more than they want a stable system. So they build on a foundation of brittle dependencies and hidden middleware friction. The result? Workflows that break the moment you put them under load. It is not a logic problem, it is an architectural one. You are assuming a wrapper can replace a protocol, but that assumption is broken. In the next 24 minutes, we are diagnosing the structural flaws of the connector model by looking past the surface. Because if you want a resilient enterprise, you do not need more connectors. You need a protocol level shift. It is time to stop building on wrappers and start building on the transport. The latency tax, diagnosing middleware friction. Every managed connector you use is a middleman. And like any middleman, it charges a tax, a performance tax you never agreed to pay. In most organizations, we treat connectors as transparent pipes, and we assume data flows from point A to point B with negligible overhead, but the reality is far more expensive. When you use a managed connector, your data is not just moving between services, it is being intercepted. It is packaged, sent to a shared Microsoft cluster, unpacked, processed, and then forwarded. This is the black box of enterprise integration. And this is where 70% of your production issues actually live. They are not in your code. They are in the throttling limits of the connector instance. Think about how these connectors actually work. Most of them rely on JSON-based REST polling. You are essentially asking the same question over and over. Is there new data? How about now? This is the slow lane of the modern enterprise. JSON is human readable. It is verbose. It is heavy. Every time you send a request, you are sending text-based headers and payloads, which means the server has to pass that text and the client has to serialize it. This creates a massive amount of CPU overhead just to move a few bytes of actual info. Now visualize the request-response loop in a distributed system. You might have a 200 millisecond latency on a single call. That does not sound like much. But as you scale, that 200 milliseconds does not stay linear. It compounds. In a complex workflow with 10 steps, that latency scales into seconds of delay, and that is in a healthy environment. When your traffic spikes, the silent failure syndrome kicks in. Standard connectors were not designed for high concurrency bursts. They have strict quotas, usually around 100 to 500 calls per minute per connection instance. If you hit that limit during a peak period, the connector does not just slow down, it throttles. It returns a 429 error. Too many requests. Your workflow then enters a retry cycle. If you have 1,000 clients all hitting that same limit, you create a retry storm. The system begins to hammer itself into the ground. The very tool designed to enable your business becomes the bottleneck that kills it. We see this constantly in e-commerce and finance. Systems that work perfectly in testing fail the moment they face real-world pressure. The flaw is not the developer's logic, it is the transport model. We are trying to run high-speed operations over a protocol designed for simple web requests. We are using a model that prioritizes human readability over machine efficiency, and we are doing it through a shared middleware layer that we do not control. This is the connector trap. It is the belief that convenience is a valid substitute for structural integrity, but the tax is too high, the latency is too unpredictable, and the lack of visibility into the black box makes troubleshooting nearly impossible. You see the failure at the end of the chain, but you cannot see the friction in the middle. To fix this, we have to look deeper than the API. We have to look at how the data is actually serialized. We have to move away from the verbose text-based world of JSON, because in a world of sub-millisecond requirements, text is the enemy. We need to talk about the transport. We need to talk about the transition from human-readable bloat to machine-optimized binary. That is where the real performance gains live, and that is where the top 1% of architects are currently moving. They are abandoning the easy button for a more disciplined approach. They are moving toward a model that does not just wrap an API, but masters the protocol. Because if speed is your first pillar, you cannot afford the middleware tax. You need to bypass the middleman entirely. You need to look at gRPC. And you need to understand why the binary revolution is the end of the connector as we know it. The binary revolution, gRPC, and the end of verbose data. The top 1% of enterprise architects are making a quiet move right now, and it starts with a total rejection of the status quo. They are abandoning REST for their internal service-to-service communication because they've realized the standard way of doing things is fundamentally broken. The way we've built connectors for the last decade was designed for a different era, but in today's world, that old model is actually incompatible with modern scale. That's why the industry is shifting toward gRPC. This isn't just another acronym for a slide deck or a minor technical tweak, but rather a 77% performance win right out of the gate. Think about that for a second. In experimental comparisons, gRPC consistently outperforms REST by nearly 80% for small payloads, and that gap only widens in difficult conditions. When you look at network constraint scenarios, gRPC can be up to 219% faster than the traditional alternatives. The reason for this jump is simple. It stops trying to talk to machines in a human language. REST relies on JSON, and the problem with JSON is that it's just text. It's a repetitive list of keys and values where you see name followed by Mirko or status followed by active over and over again. To a machine, all of that extra text is just bloat that gets in the way of the actual work. The machine doesn't need to read the word name every single time it receives a record because it only needs the raw data to execute the command. This is where the binary revolution changes everything. Instead of sending verbose text, gRPC uses protocol buffers, or protobuf, to send machine-optimized binary payloads. It takes an 83-byte JSON message and shrinks it down to just 33 bytes, which represents a 60% reduction in wire size. In a high-volume environment where every millisecond counts, those saved bytes are pure gold for your infrastructure. Your payloads become 10 times smaller while your data receive speed becomes 7 times faster, but the real dividend isn't just what happens on the wire. The real win is in the compute. Because protobuf is binary, the serialization and deserialization process is incredibly efficient for the processor to handle. It uses 50 to 80% less CPU than parsing JSON, which is often the difference between a struggling cluster and a stable one in a distributed system. By changing the fundamental how of data movement, organizations are seeing a 34% reduction in memory consumption across the board. They're getting more work out of the hardware they already pay for, and they're finally solving the persistent issue of interface drift. Interface drift is what kills standard connectors. So you update a single field in one service, but the connector doesn't know about the change, and the entire workflow breaks without warning. gRPC solves this through a schema-first design where you define the contract in a .proto file and generate the code directly from that schema. It's strongly typed at the protocol level, so if the data doesn't match the contract, the system catches the error before the message is even sent. This prevents the silent failures that haunt managed integrations and replaces the guesswork of REST with the discipline of a strict contract. We're seeing Fortune 500 companies move 40 to 50% of their microservices stacks to this model, especially in the worlds of finance and AI. When you're handling 50,000 to 100,000 requests per second per core, you simply cannot afford to be verbose. You can't afford the overhead of text-based parsing, and you need a transport layer that actually understands how the machine thinks. This marks the end of the black box connector for high-throughput systems. It's a shift from a wrapper that hides complexity to a protocol that masters efficiency, and it's about taking total control of the transport layer. But speed is only the first pillar of this transformation. Raw throughput doesn't matter if your connection is fragile or if every request requires a brand new handshake. If every burst of traffic causes a reconnection storm, you're still operating in a legacy mindset that limits your potential. Resilience isn't just about how fast you move the data, but rather how you maintain the path between your services. Because if speed is the first pillar, then resilience through persistent connection is the second. We need to look past the individual request and start looking at the stream. Beyond polling, the power of persistent streams. The industry has been conditioned to believe that work starts with a request, but that assumption is fundamentally broken for the modern enterprise. We've built our entire integration strategy around the pull model, where a client asks a question and the server provides an answer. In a world of real-time context, waiting for a request to come in means you're already too late to the conversation. Yet, this is exactly how almost every standard connector operates today. They rely on polling, which means they check for updates at fixed intervals like every 5 seconds or every minute. It feels like automation when you look at the dashboard, but in reality, it's a massive waste of your technical resources. Think about the math for a moment. If you have 1,000 clients all polling a single endpoint every second, you aren't just making 1,000 requests. You're generating over 1 million requests every single minute, and most of those requests return absolutely nothing. The server just says no new data or still nothing over and over again. This creates a massive amount of empty traffic that spikes your server load by 10 times compared to a persistent stream. It's a legacy habit from a time when connections were expensive to keep open, but today, the opposite is actually true. Maintaining a connection is cheap, while the act of re-establishing one over and over is what costs you. This is why the gold standard is shifting toward WebSockets and the upcoming 2026 standard known as Web Transport. With a WebSocket, you establish a persistent bidirectional channel where the handshake only happens once at the very beginning. After that initial connection, the overhead drops to just 2 bytes per frame, and the server doesn't wait for a question anymore. It pushes the answer the millisecond the data exists in the system. This is the instant-on enterprise where data pushes to the user instead of waiting for a manual pull. But even WebSockets have a flaw because they run over TCP. TCP has a problem called head-of-line blocking, which means if one packet gets lost in the stream, the entire connection stops. Everything waits for that one lost piece to be retransmitted, and in a high-frequency environment, this creates microstutters and latency spikes you can't explain. That's where Web Transport changes the game. It's built on HTTP3 and the Quickie protocol, and because it's UDP-based, it handles multiple streams independently. If one stream loses a packet, the other streams keep moving, and the system doesn't freeze up while it waits. It also enables something called seamless mobility. Standard connectors drop the moment a user switches networks, so if you move from Wi-Fi to 5G, the TCP connection breaks and the session dies. But QUIC-based protocols support connection migration at the transport level, which means the IP address can change while the session survives. This is critical for the mobile-first workforce because you can't have your integration layer failing just because someone walked out of the office. By moving to persistent streams, you're doing more than just reducing latency, and you're actually changing the relationship between your services. You're moving from a reactive model to a proactive one. You're eliminating the 150-byte header overhead of every single polling request and replacing it with a continuous 8-byte flow of real-time context. This is how you handle millions of concurrent users with sub-100 millisecond delivery. You stop asking, "Are we there yet?" and you start listening to the heartbeat of the system. It's a shift from fragmented requests to a unified data flow, but there is a catch you need to consider. Raw speed and persistent streams are powerful, but they're also dangerous if you aren't prepared. When you open the fire hose, you have to be able to handle the pressure on the other end. If your backend can't keep up with the stream, or if a service goes down while the data is pushing, your high-speed protocol becomes a liability. You need a safety net because speed without resilience is just a faster way to fail. We need to look at how we protect the system from the very traffic we've just enabled. We need to talk about asynchronous resilience. The safety net, asynchronous resilience patterns. Connecting two high-speed services directly is a liability. It is a point of failure just waiting to happen. In a perfect world, every service is always available. But the enterprise is not a perfect world. It is a messy environment of network blips, database locks, and unexpected maintenance windows. If you rely on a direct synchronous path between your stream and your backend, you have built a glass house. One minor crack in the receiving end shatters the entire pipeline. This is where managed connectors usually fail. They assume the path is clear. When it isn't, they just stop. Or worse, they trigger a retry storm. Think about what happens when a backend service slows down. The connector sees a timeout and tries again, but it is not alone in that process. Thousands of other connection instances are doing the exact same thing at the exact same time. You are effectively launching a DDoS attack against your own infrastructure. You are hammering a failing service until it completely collapses. To move beyond this, we have to implement asynchronous resilience patterns. We have to decouple the burst from the backend. The gold standard for this is queue fronting everything. Whether you use RabbitMQ, Amazon SQS, or Azure Service Bus, the principle is the same. You place a durable buffer between the protocol and the logic. When the data arrives at protocol speed, it hits the queue first. The queue does not care if the backend is busy. It just accepts the message and holds it until the system is ready to process. The runtime pivot, built-in versus managed logic. Most architects assume that because their logic app is in Azure, their data stays in Azure. But with managed connectors, that's not true. These connectors are essentially SaaS products that live on a shared cluster outside your virtual network. When your workflow triggers a managed connector, the data leaves your VNet and travels across the public internet to reach that shared cluster. Then it travels back. This is a fundamental networking flaw. It's a breach of the zero trust model. If you have a private SQL database, you've probably used the on-premises data gateway to bridge this gap. But that gateway is another bottleneck. It's another layer of serialization that adds latency you don't need. The solution is the runtime pivot. We have to move from managed logic to built-in logic. In the Microsoft ecosystem, this means moving to Logic Apps Standard. This version runs on a dedicated app service plan. It's single tenant. The connectors aren't external wrappers anymore. They are built-in or in-app. They execute directly on your compute instance. This changes everything for your security posture. Because the connector is running in your process, it respects your VNet routing natively. There is no public egress. Your data stays within your private boundary. This shift also eliminates the need for the data gateway for many core services. If you're connecting to SQL or SAP, you can use VNet peering or ExpressRoute instead. It's about moving the logic to the data rather than sending the data to the logic. The AI horizon, orchestration at protocol speed. The coming wave of autonomous AI agents is the final nail in the coffin for standard connectors. We are moving toward a world of agentic workflows. In this new model, machines aren't just following a static path. They are making real-time decisions. They are negotiating with other services. They are taking turns in a complex digital conversation. But here's the problem. If your integration layer relies on a legacy connector with a 500 millisecond overhead, your AI strategy is dead on arrival. High-functioning agents require sub-200 millisecond round trips for natural turn-taking, and if the plumbing takes longer than the thinking, the entire orchestration falls apart. The agent loses context. The decision-making loop becomes too slow to be useful. This is the shift from low-code to pro-code integration. The next generation of successful architects won't just be experts in drag-and-drop interfaces, they will be protocol experts. They will understand the nuances of binary, serialization, and QUIC-based transport because that is where the competitive advantage lives now. Enterprises that integrate AI at the protocol level are seeing a 10.3 times return on investment. The reason is simple. The data is ready the moment the model needs it. There is no middleman, no text-based parsing text, no black box throttling to slow down the inference. We are preparing for a world where machine-initiated traffic outweighs human visits by 40%. Your model needs to be built for this machine-to-machine economy. If you continue to rely on surface-level wrappers, you are essentially asking a high-speed AI to communicate through a dial-up modem. And that friction will show up directly in your bottom line. True orchestration requires speed that connectors simply cannot provide. It requires a direct line to the data where the plumbing doesn't get in the way of the intelligence. This is the new standard, and it starts with the transport. The transformation is clear. You don't need more connectors. You need better protocols. You need to reclaim your architectural sovereignty from the easy button illusion. Here is your challenge for this week. Audit just one high-volume workflow in your environment and look for the managed connector that is currently your biggest bottleneck. Replace it. Shift to a built-in queue-fronted stream. Watch the latency drop and watch the reliability stabilize as you remove the unnecessary layers. If this changed how you think about enterprise integration, follow me, Mirko Peters, on LinkedIn. I want to hear about your migration struggles and your wins. Share this with your team, especially if you're dealing with these bottlenecks right now. And if you want more of this, leave a review. It helps more people find this information. Stop building on wrappers. Start building on the protocol. That is the only way to scale.